Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future on YouTube. Today we are going to start looking at the actual material after last week's appetizer that hopefully got you excited about the topic. And we're going to start with the cloud storage parts. Data needs to be stored somewhere, right? So I want also to say that we have here a moderator, and everybody can ask questions at any time in the lecture hall. You can interrupt me. Everybody on Zoom can also ask questions at any time. You can directly write your question in the chat, and then we can I can answer a question. So Dalia will interrupt me on your behalf, and it's always fine to ask questions. We are in a university. We are learning. Maybe I won't know the answer, then I just check later and get back to you. There is no such thing as a stupid question. We are learning, and there should be no hesitation in this regards. So I like to start with the real world. We have all these data sets out there. One of them, so previous to the Vera Rubin Observatory that is about to be started, we have this older data set in the Sloan Digital Sky Survey, currently in phase 5, actually about to be completed. By curiosity, I looked at the data sets, the phase 4 data set, and that was the amount of data that I saw in there, 273 terabytes of data. This doesn't fit on a hard drive, even the latest hard drive that I showed you, that was 245 terabytes. So it doesn't fit. And the data sets that are going to arrive are even in the petabyte range and even hundreds of petabytes. So we have here 680,000 directories, 176 million files. This is absolutely gigantic. And so the topic of this first lecture is how do we even store that, since it doesn't fit on a single laptop? That's what we are going to talk about. I hope that this clicker is not again on strike. But normally, if I click, that goes to the next slide. Yes, maybe I need to not go too far from the computer. So how do we deal with all of that data? Well, at first, the engineers that first faced a problem like that, so these were engineers of companies like Google, Twitter, Facebook, Yahoo, they thought of using existing systems, right? That's usually the first idea you have. You look for existing systems and you see if you can do something with that. So we have relational databases to store data. This is the most classical kind of database system that you can imagine, fits on a single machine. So a first idea would be to make it fit on several machines by just duplicating, right? You could install relational databases on plenty of different machines. And at first, it sounds like good news because one of the messages in the lecture is that 99% of what existed before big data in the good old times can be reused. And what I mean is a lot can be reused. Selection, projection, grouping, sorting, joining that we saw in the 1970s, they are still here in big data. Declarative and functional languages, SQL is still going to be here, optimization, query plans, indices, it's still going to be here. That's not going away. Tables, rows, columns, primary keys, we're going to see that all over the place again in this course. That's actually pretty good news, right? Because it means everything you've been learning is not thrown away. But there are a few things that are going to change. And you might remember these normal forms, the very scary normal form, second normal form, third normal form, fourth, fifth, sixth, 3.5th normal form. This is all going away. We're going to just drop it and look at denormalized data. So it means that the relational integrity or tabular integrity, I call it relational integrity, also now in the textbook, and last week, domain integrity, atomic integrity, also known as the first normal form, this is all going away. The higher normal forms, this is all going away. What we will see instead is data that breaks the rules. And we'll learn in which way the data actually breaks the rules. The first way it's going to break the rules is that the data is going to be heterogeneous. So it means you can have in the same column plenty of different types of values. That's totally fine. You might have missing values, more attributes in some records. That's totally fine. The second way that we are going to break the rules, and in particular the atomic integrity, first normal form, the data is going to be nested. Inception, a table in a table in a table in a table in a table, a dream in a dream in a dream in a dream. So we are going to break this rule, and that means that the data is denormalized. With denormalized, we mean these two things. And or, right? So it can be just in this way, it can be just in this way, it can be in both ways. In any case, we just call it denormalized. And denormalized data is actually quite cool because that gives us different shapes of data. So here, obviously I need to click in here, but I have so many different cascading windows that give this view that I need to find which one. There you go. And so speaking of denormalization, what data shape do you think we get if we denormalize a table? You can just go to menti.com, so the website you see in there, and you can type 66535456 and give your answer in there. I already see an overwhelming majority of people that tell me 3. Probably mentioned it very briefly last week, so it's very nice to see that you remember what I told you. Lots of 3s. And some people like the last answer. You cannot denormalize the table denormalizes you. Okay. The 3s win, and indeed the 3s are the correct answer. More exactly, when you denormalize the table, you get plenty of 3s. You get a collection of 3s. Every record becomes a 3, right? And we see that a record in a relational table is just a flat and homogeneous tree. Flat in the sense that there's nothing nested, and homogeneous in the sense that all the records in the table have exactly the same schema, right? So indeed, when we denormalize the data, we get trees. And we'll see that as a consequence, JSON and XML are actually a denormalized form of data that we call semi-structured data. All right, so how do we do all of that? We are not going to start from scratch because there's a lot of knowledge that we get from the 70s and later. But we are still going to reconstruct things bottom up. So it means that this stack that we get that already existed in the 70s, the stack is what a relational database system is made of. We are going to take the components, take it in pieces, like an IKEA piece of furniture, and we are going to rebuild it. So you need to understand that this stack that we are going to rebuild was very monolithic in the old relational database systems. Why? Because it was just something you install on a single machine and that's it, right? So it's just a huge block. You just install it, drop it, like you install PostgreSQL, and that's it. But let's see what there is inside. This is what there is inside. And in fact, all of these components that we see here is going to be what we will do during this semester. We're going to start here today, then we're going to go up the stack. So very, very briefly, just so that you understand the levels, the storage level is where you store the data. Can be on your laptop, that's perfectly fine. Can be on some network file systems. Then we look next week at HDFS. Do you know what HDFS means, anybody? Yes? The Hadoop file system, the Hadoop distributed file system, absolutely. This is, who heard of Hadoop before? Many of you who never heard of Hadoop. Okay, it's the name of the elephant toy of Doc Cutting's son. This is how it was named. So we look into this next week. S3, who heard of S3? All right, that's the simple storage service of Amazon. So that's what we'll look into today. Azure Blob Storage, anybody? All right, it's the same thing or kind of the same category of products by Azure. There's also Google Cloud Storage and many others. All right, so that's what we'll do today. Then we'll see that this storage system store bits, right? It just store bits, and we need to encode whatever data we have, which might be text or binary, into bits. So we'll quickly, maybe not so much, but very quickly see that there's different encodings and even binary formats. Then we look at syntax, which is one level above, because the goal of syntax is to represent data as text. And we'll see that, so CSV, I'm sure you all know, XML and JSON, that, like I said, these are trees. CSV is for tables. RDF XML, that would be for graphs. And there's others, like Turtle is also for graphs. XBRL will be for cubes. So there's plenty of syntax that just represents data in any shape as text. And this is what we will store in the end on the storage system. So you see it's modular, right? So again, this will be encoded and then stored. Now, if we move one level up, we are going to model that data with abstractions, because otherwise it's just syntax. And we are going to, so the relational model, we did it last week as a brush up. We'll look at XML and JSON models, we'll look at graph models, we'll look at cubes models during the semester. Models are very important because, as you might imagine, when you open data, when you take data from the storage layer, it is text. It's obvious that you're not going to process it like this in memory. Instead, you're going to optimize the way it's stored in memory as graphs, as trees, and so on. It's actual graphs and actual trees that you'll have in memory. And this is what the data model is for. It gives you the skeleton based on which you can efficiently store the data in memory after you have parsed it from the storage layer. Then we have the validation. We'll see that on the contrary to relational databases, data might not be validated. This is something we can do separately. And so we'll look at XML schema, JSON, which is a pedagogical way to look at schemas. Relational schemas, you already know, XBRL taxonomies. These are the schemas for cubes, and so on. So the validation checks that the structure of the data is according to our wish. For example, you might want to check that all the trees in a collection share the same schema, right? That would be a homogeneous collection of trees. Would still be denormalized because it's nested with trees, but it would be homogeneous. By the way, when we have homogeneous collections of trees, we get data frames. Who heard of data frames? Who heard of Pandas data frames? Many of you who heard of Spark data frames? All right, so we'll see that data frames are just a homogeneous collection of trees. All right, that's pretty much what it is. Then the exciting part is going to start when we let this data flow all over the clusters. And we'll look first at the first generation of processing systems, MapReduce. Who heard of MapReduce? Right, it's pretty cool. Then the second generation, who knows Apache Spark? Many of you as well. So that's the second generation. And we look at all of them and see the progress that was made and the ideas behind this. And then we'll talk a bit about clusters. Who heard of EC2? Right, that's Amazon's way of booking machines, virtual machines in the cloud. So, all right, these are all some pieces of the puzzle. There's also many others, right? But again, we are learning one, and you will see that learning any other technology is a walk in the park after you know the basics. My goal is, of course, I'm using today's technologies, but that's not my goal. My goal is to prepare you for the next decades of evolution. Maybe some of you will invent new systems based on that, but the ideas are what matters in here. Then we are going to look at optimization. Surprisingly or unsurprisingly, the techniques are similar to what you would see in a relational database, and we'll rehearse that a little bit. We'll look, so key value stores today and tomorrow, hash indices, B+ trees. Who heard of B+ trees? Hash indices? All right, so you'll see they will also be here in big data. We'll study them a little bit. And there's also geographical indices when you store geographical data, spatial indices, and so on and so on and so on. So many indices. Indices are like magic. You have a query that takes an hour, you add an index, it just takes a few milliseconds. That is absolutely very powerful to use them and to understand them. Then if we continue to go up, we have data stores. So here you start having a complete product that offers a lot of features, but a data store would not be a full-fledged database system because it's still missing a query language, right? So it would be the idea that you have some model, it's stored in some way, typically with ETL, you have to import the data in there, and then it manages it for you. You can communicate with it with an API to query or update the data, right? Then, to make it complete, we'll see that we can have functional and declarative query languages. SQL is one of them, and we will also use it again. But what you need to understand is that SQL was made for tables, and only for tables. People tried to hit it with a hammer to make it work with trees and graphs and others. It just doesn't work, right? When you have a query language, it has to be made for the shape of data that you are dealing with. The problem, as we will see, is that not everything has been standardized. SQL, everybody agrees. Anybody in their right mind will agree that SQL is the language to use for tables. For graph, this is ongoing, and now it's made a lot of progress. Just 1 or 2 years, in the past 1 or 2 years, there's been standardization efforts. So now it's really, really in a very good place to have a standardized language for graphs. And now many of the database vendors are converting their systems to follow the new standards. Then we'll see for cubes, there's MDX, multidimensional expressions, even though I'm not going to scare you too much with too many languages. And for trees, it's an absolute catastrophe. I'm trying to keep track because there's already 30 plus languages that get designed, and every couple of months, somebody reinvents yet another language. They really all use the same ideas. So I'm going to teach you one that I co-designed, one actually of the first ones, and then you can learn any one of these, and whatever gets standardized in the end, you will be able to quickly learn it. Again, it's all about the ideas. All right. And this is, again, it's cutting edge. This is ongoing. This is still something that is alive and evolving very fast. All right. REST APIs I'll talk about today. This is not a query language. It's more of an interface between layers. And finally, and here it's a bit out of bounds for this course, of course, there's the user interface. That's for people who interact with the system without any knowledge of querying. They might just drag and drop stuff like forms or masks or fancy user interfaces. Spreadsheet software that is connected to a database, data business analytics tools. ChatGPT even belongs to that. Now you can even interact with data as ChatGPT. Of course, it's desirable to go via query languages in between. I'm going to tell you something. Actually, I find it amazing. When I feed the exam questions, the querying exam questions to ChatGPT, it correctly solves them. So you get the query together with a huge explanation on why each component of the query and so on. Actually, that's great because it means you can practice using such systems to drive you. With care, because they hallucinate, so you always need to double check everything that they tell you. FL is here for this goal. Okay, but we need to start somewhere because I'm not going to do all of the 14 weeks today. So we are going to start with storage right now. So the way it starts is with a question. Again, I don't know, I need to click somewhere and probably the question will display. So let's see, yes. So my question to you is, what is there in a data center? Is it top secret? Nobody knows because it's just some secret basis like Area 51. Or is it one really big machine with 1,000 core CPU, 100 petabyte disks, and 1 petabyte of memory? Or is it plenty of small chip machines? Or is it a giant quantum computer with an array of 54 qubits? There was actually 56 in Sycamore, but 2 of them somehow burnt. Why, for Feynman's sake, would we wait for trillions of core hours to get an answer? It's the power of quantum computing. It's not a quantum computing course. I might say a few words at the end. Quantum computers are not there. We can still not factor high numbers, but it's still interesting to know on the high level. But anyway, we have a dominating answer, and in fact, it's the correct one. We'll see that it's plenty of small, cheap machines. It's almost disappointing, right? When you hear of data centers and you think this is probably something fancy, but no, it's just a bunch of small, cheap machines. That's all there really is in there. And we need these machines because data needs to be stored somewhere. Because, you know, in everyday life, people say the cloud, you know, I store my data in the cloud, it's somewhere in the cloud, but the cloud doesn't exist physically. The cloud is eventually machines. You upload it through the internet and so on, but then it's going to land on disks, inevitably, right? So data needs to be stored somewhere. You might have heard information is physical. Whoever heard that? Information is physical. It's a saying. Now what you hear among quantum physicists is that physics is informational. Seems like information theory, in fact, might even be the fundament of our universe. But anyway, physics, information is physical, and so we need to store the data somewhere. There are two approaches. So this is a very important slide to structure your thoughts. Two approaches to storing data. The first data, which you see on the left, is the data-independent approach that Edgar Code launched in the 1970s, that many of the database systems follow, which is the idea that before you can query data, you need to import it in your system. So you need at some point to put the data in there, and then you can query it. This process of putting the data in there is called extract, transform, load. These systems very carefully hide the way it's stored. It is eventually stored on disk, but you don't see how. This is hidden. What is it called? Data independence. Exactly, that's data independence. PostgreSQL is like that. You need to import the data. We have script, of course, that we give you that import the data. And for the ones of you who feel adventurous, you can try to locate on your hard drive where this is stored. Try to go to inside the Docker and find the directory, and you will see these are actually files. But the user of PostgreSQL never gets to see them. You just interact with tables and with SQL. So this is one way, the classical way from the 1970s. And then we have another way that emerged more recently because of the difficulties we have to scale, which is the data lake. The data lake, in fact, strictly speaking, it breaks data independence. Because now you see the files, you see how it is stored. So it's a compromise that we make in order to scale. It breaks data independence. It means that your data is just on a file system. You just drop the data in there as files, and then you write scripts like Pandas, Python, and all these kind of things, and Spark, and you query the data reading from the file system. In fact, in a way, what we are doing here that we were kind of forced to do because there was no other way is bringing us back to the 60s, because this is how we were doing it in the 60s before there were the relational database systems. So what is the goal now that everybody is pursuing, and there's been a lot of progress recently, is to take this, which is the situation we have right now, and everybody is now pushing to bring us back to here, but with petabytes of data. Because that we don't know how to do yet with hundreds of petabytes of data, but we are getting there. Every year, there is a bit of progress, and I will explain the challenges of getting back there. But this is the reason why today, plenty of companies use these fancy data lakes. It's even a buzzword, where you put your data and you query it from there. Okay? So speaking of file systems, because right now we are going to be focusing on data lakes, this approach, we need a file system. So in a file system, you know that the files are typically stored in a hierarchy of directories, and then the leaves of this hierarchy are the files. This in itself, by the way, is a model and an abstraction, right? Because the directories and files, they don't really exist. On the disk, you just have zeros and ones. So that's already a model that exposes the disk as an abstract tree of directories and files. For those of you who took system software of such courses, you have inodes and all kinds of implementation details. On the high level, you just have a hierarchy of trees and files. The second thing that then maybe less people know or are aware of is that the files are stored in blocks on the disk. Who knows roughly the size of a block like this on the laptops right here? The order of magnitude? Kilobytes, yes, I heard kilobytes, and indeed that's kilobytes, right? So did you want to also say this? Kilobytes? Yes? 4,096. 4,000. 4,096 bytes. Yep, you're correct. Absolutely. This is a very common size for the blocks. It's 4 kilobytes, basically. Absolutely. Very common. Of course, the file systems can be different, right? Some of them might say 2 kilobytes, other 8, but absolutely 4 kilobytes is the most frequent size for the blocks. Why do we do that? Remember what I told you about throughput and latency? If we would read bit by bit, 1 bit at a time, you would have to wait every time to reach the bit. So imagine opening a Word file, like even a small file you on your computer, the time it would take if you read it bit by bit. The blocks solve that problem. When you read from the disk, you read in a single go 4,000 bytes. Bytes, 8 bits, right, just to make sure. So this is why we have blocks. And blocks, they are less known, but they are actually exposed. You have a way to see the block on the file system. But of course, when you use higher level software like spreadsheet or anything, or even databases, you don't need to worry about the blocks. But the reason you need to know about this is that we'll have them also in big data systems. So the blocks are going to be an important component of the system we are going to build. So now you might think, okay, we have local storage. How do I scale by storing on multiple disks and having many people or computer access it? Well, why don't I just buy a network switch and a few hard drives, and I just put them in the network, and then I let the thousands of people connect to these disks and use them? But that actually breaks. That just doesn't work. You cannot have so many people or so many computers accessing the disk at the same time. So you might have, for a small number of people, you might have a small network attached storage. Who has that at home? They have some hard drives they connect to, right? It's quite popular. Who has RAID? Right? Redundant array of inexpensive disks. We'll see we don't need RAID actually, but I'll tell you why we don't need RAID. But it is one way to combine multiple disks and avoid errors. Wide area network, this is where it breaks. You cannot just have a disk, for example, a disk that everybody would connect to at ETH, that's a no-go. That just doesn't work. And for physical reasons. And then another aspect of it is the number of files. Who does backups regularly? Who doesn't do backups? You really have to start now. Do a backup, especially of your projects. If you do a backup, you might see the number of files that are backed up. And typically, the order of magnitude that you will see is maybe thousands, probably even tens of thousands or hundreds of thousands. That's typically what you have on a computer, maybe millions. But anything beyond that, if you try to have billions of files, this is where things again start breaking, right? So if you're a database, or if you're a cloud provider and you want to store things for the whole world, you're probably going to have billions or even trillions of files. And as you can imagine, S3 is not just a simple set of disks connected to the internet, right? There's more to it to make it work. So we see that the systems we have, they just break. We are hitting some limits and we need something new. And so here I want to use an analogy with electric cars. Do you know how we kind of solved the price, keeping the price acceptable for batteries in electric car? Did we completely redesign the car engine to consume less power? Did we completely redesign the battery so that it has more range? Do we just assemble plenty of cheap, widespread, standard 18650 batteries? Or you're not allowed to tell us, maybe? Oh, a lot of people interned, right? I actually know that a lot of you actually, who is working part-time or something? Right, quite a few of you, okay. And again, the majority is correct, right? You're such a great class. Indeed, this is what is done. We just assembled the standard batteries. 18650 is just the dimension of these batteries. And yeah, that's what there is in a battery in the cars. That diminishes the price. Who sees the parallel with the data centers? It's exactly the same idea. We just reproduce plenty of small and cheap elements in large quantities. So what we are going to do, based on all of these ideas, is the first thing we are going to do for our cloud storage system. Imagine a service for the whole world. First, we throw away the hierarchy, too complex. The hierarchy of directories and so on, that's a data structure. So let's throw away the hierarchy and flatten everything. And second, we simplify the data model. So something super simple, key value. We just store files and every file is identified with some ID, right? That's the idea, plain, simple. We'll call these files objects. So this thing that you see right here, we're going to call it an object. And this is why we call it object storage. And what we get is a very simple, flat, global key value model. We store objects for the whole world identified with IDs, and that's it. That's what S3 is, and many other storage systems as a service. So we're slowly getting there with the ideas, but I need to tell you a few more things to justify why we are doing it in this way. Why are we flattening the hierarchy of files? Why are we building plenty of small, cheap computers into a data center? Well, there are several ways when you want to scale, to make the amount of data you're dealing with scale. The first idea that usually comes to mind when you have a computer and the data doesn't fit is just to buy a bigger computer, right? It has a larger drive and more memory and more CPU cores, maybe even faster CPUs. If it's still not enough, what do? You just buy an even greater computer with more memory and more disk and so on, right? But the problem is that it has its limits, because we saw that beyond today 245 terabytes, you can't go beyond that. Maybe you can plug a few disks to your machine, 2 or 3. You also know that the memory is very costly. You see that when you try to order more, when you buy a computer, and at some point it doesn't even exist, the quantities of memories you need. So there is another approach. So this first approach is called scaling up, right? So you scale up if you take a bigger machine, and you scale down if you take a smaller machine. Scale up, scale down. Another approach is scaling out. Scaling out means you keep your machine, but you buy another one, and another one, and another one, and even plenty of more machines. That is called scaling out. Guess how it's called to do the opposite? Scaling in. You scale in, right? You scale in, and you scale out. This is the second approach to working with more data. And in fact, if you think about the economics of that, how much it costs to scale up or to scale out, then it dawns on you that scaling out grows linearly, at least if you keep it reasonable, it grows linearly, and scaling up is exponential, and I would even say hyperbolic, because there's probably an asymptote. Because if you think of it scaling up, if you try to build a computer with a petabyte hard drive and with, let's say, a petabyte of memory, that's probably going to cost you billions of dollars. Why? Because you need to hire a whole R&D department that's going to design the new technology and so on, and maybe even more money thrown at it. You manage to get one in 10 years. Only one. And then if you want to do it even more, you can't even do it, right? There's just not the technology today. So we hit a wall. When we try to scale up, there are just limits to what you can do. Scaling out, however, you can just buy more and more and more and more and more machines, right? And here again, in terms of economics, it's almost microeconomics. Locally, that grows linearly. Of course, when you arrive at the scale of the planet, that's different, right? You at some point, you run out of resources. But locally, with a few machines or at the scale of a data center, you just buy more and more and more machines. And at first, it is linear. For whom is that clear? Okay. But there is a third way. And the third way is my favorite way. And this is the one way that I would like to come first in your minds. If you create a startup and you need to start somewhere with the data, there is the first thing you should do before you try to buy more machines or go to the cloud or buy more expensive machines. And that approach is to optimize your code, find better ways to store the data. Maybe you can eliminate redundancy, you can compress, you find ways in your code to accelerate the code by writing it more efficiently. That is always the first thing that you should do. Always try to work with one machine, one laptop, your laptop, and that's where it starts. And if that doesn't work, then you can go and scale out. I have as an example one of my former students who did a great master's thesis, actually contributed to the RumbleDB that you're going to use this semester. His name is Marco. So Marco told me he had a computer, but that computer was limited in memory. It had like maybe 4 gigabytes, it was an old computer, 4 gigabytes of memory, limited disk and so on. And so Marco was worried, you know, that might be not enough. I need more power for the master's thesis. And I said, no, you don't need more than that. This is perfect. This is perfect because this is going to force you to write efficient code and to think about the way you store the data. And there is great power in this because when you manage to write your code efficiently to squeeze as much as you can on a single machine and on every gigabyte of memory, you can then scale out, and then everything you did locally is going to scale to the data center. So if you manage to store 100 more times data in your laptop, then you will also be able to store 100 more times data in the data center once you do that. So this is where everything starts. And I love this quote that you can only have a second computer once you've shown you know how to use the first one. That is a very, very important wisdom. I'll come back a little bit on that, right? So that should be always your first thought. How do I optimize things with the first computer? And then we can scale out. And when we scale out, we will get systems like S3, and this is now the approach that we favor right here. Which brings us to data centers, because now you know in a data center there is plenty of small and cheap machines. Checking the time because I don't want to infringe on the break. By the way, we're going to have visit during the break. You have presentation, I think, from FIS and from cars, the ETH students who broke the world record in the car acceleration. So anyway, keep being excited about that until the break, and then you'll hear more. But coming back to the data centers, typically in a data center, we have between thousands of machines, tens of thousands of machines. Right? Typical number is 10,000. And I put here an upper bound of 100,000. Does anybody know or can guess why we have this upper bound of 100,000 in a data center, roughly? Yes, maybe yes? Yes, energy power, that's exactly it. Yeah, you start having energy problems and cooling problems. Just to give you an example, we went a couple of years ago to a field trip with the class in a data center in the north of Zurich, and to see how it looked like. And turns out that a data center like that, it wasn't even a large, you know, as large as others. The power of that data center was about as much as the airport of Zurich, just to give you the order of magnitude of what it consumes, and also the cooling of the computers that you want to keep cold. Now, of course, there's a few optimizations you can do, because since the computers in a data center produce a lot of heat, then you can use that heat to actually heat all of the people living around the data center, right? And this is actually done. There's a reuse of the heat created by the data centers to heat the houses and the apartments of the neighborhoods. But that means that there is a physical limit, right? And there is a limit that is very hard to go beyond, and that stops. That basically stops here. We don't know all the numbers of the companies, but to date, I'm not aware of any data center with more than 100,000 machines at the same location. Okay, then we have cores per machine. Typically, I put the orders of magnitudes between 1 and 200. Here, you need to pay attention to the fact that typically when you book in a data center, you book virtual machines, right, that themselves run on physical machines. And you need to remember that because of hyper-threading, the number of actual cores that you get, the virtual cores, is double the number of physical cores, right? So you also need to have this in mind, which is, again, a more efficient use of the physical cores. Storage, now I increased that to the order of magnitude of 200 terabytes because of that drive that I've shown you, that we are now in this range. It's probably going to keep increasing in the coming years. Then for the memory, we find machines that go all the way to as high as 24 terabytes. I actually looked them up on online. When you try to see in the catalog of some online shops, you can see the sort of machines that you get. The network can go very high too. I think it's very common to have 400 gigabits per second. 800 gigabits per second is now slowly rolling out. And I think some people are trying to push to 1,600. So here too, it's making progress. We'll see here that this network bandwidth that is limited, that has an impact on the design of the system. So HDFS and so on that we are going to look into, that's something we need to keep in mind. Now I might disappoint you because I showed you a slide of the data center with all these, plenty of cheap small machines, and they look like the computers you have at home or your laptop. That's actually absolutely not what a data center looks like. We don't put the computers just like that. Instead, we pile them up like this. So we have these towers right here that you find in data centers, and we pile them up. The machines are just on top of each other like this, and we call this a rack. And when you go to a data center, you basically just have plenty of racks like this. This is what a data center rooms look like. Just rack, one after the other. And that's what you have. It's standardized, so the height of these towers is standardized, and there's rack units, which is all when you put it inside, there's certain heights that the individual machines can have. We use RU for rack units. What can you pile up in there? Well, first, servers, machines. Very often, we call them nodes. That's probably because of the network topology, network people. So if I say a node, it's the same thing as a machine. We also have storage nodes, meaning we just have a level with just hard disks that are connected to the rest of the rack. We might have network switches and routers that also take one layer in here, and so on and so on, right? So this is how we pile them up. And so you see what it looks like. This is actually one machine, one node, just flat so that it can be piled up. Okay, who already saw this? Right, who sees this for the first time? Okay, so now you know what there is in a data center and what it looks like. And that's basically it. And the people who deal with the machines, of course, they can access them remotely. I also saw in some places, IBM, I think, and these kind of places, but probably everywhere, that the engineers can also come with their little laptops and connect the little laptop to these nodes, and then they can access them, right? Probably today it's more common to just connect remotely to the nodes to configure them and fix the issues. Okay. So this is the hardware. This is what there is physically in a data center. And right after the break, we are going to start looking at a logical level on Amazon S3. We are going to look at what it is, how it is exposed to the users. And then I'll tell you a bit about REST APIs and so on. So we are going to have our break soon in 2 minutes, but that gives us a bit of time to set up the talks. So now you're basically free to do whatever you want. If you want to go have a break, go get some coffee, you can. If you're interested in the talks by FIS and about the cars, then you can also stay here.